Think about the last time you accidentally swallowed a mouthful of ocean water. That sharp, stinging saltiness, it's a sensory shock. Now, compare that to the same experience with a mountain stream, clear, crisp, and completely fresh. It is a strange paradox, really. Why is the sea so consistently salty, while our rivers and lakes remain mostly fresh? Now, if rivers are the delivery system for salt, why isn't the delivery truck itself salty? Today, we're going to reveal the hidden salt trap that turns the ocean into a giant mineral repository. The ocean covers 70% of the Earth's surface and accounts for 97% of all water on the planet, yet only 3.5% of that water is actually salt. 3.5% sounds like a tiny fraction, but it's enough to change the very chemistry of our world. Let's go back billions of years. The world was a chaotic, molten mess. The first oceans formed from volcanic steam and asteroid impacts as the planet cooled and gases condensed into liquid water. In those earliest days, this water was fresh, much like the rainwater falling outside your window today. It's a strange thought, isn't it, that the vast blue expanse we know now was once a freshwater paradise. But the chemistry of our planet was shifting. Over 250 million years ago, Earth's oceans already possessed much higher salinity levels than they do today. The water was thicker, heavier, and far more saturated with minerals. We're witnessing the beginning of a great accumulation, a process that doesn't happen overnight, but unfolds over eons of geological time. And while the surface was churning, something secret was happening deep below, where underwater volcanoes were adding a hidden ingredient to the mixture. It all starts with something as simple as a rain shower, but if you look closer, the water falling from the sky is not actually pure. Rainwater is slightly acidic because it absorbs carbon dioxide from the atmosphere, creating a chemical reaction that forms a weak carbonic acid. Now, this is where the chemistry of the landscape begins. As this acidic rainwater hits the ground, it doesn't just soak in, it dissolves minerals, specifically sodium and chloride, from the surrounding rocks. These two elements are the essential building blocks of salt. How does this happen on such a massive scale? Well, it's essentially a tiny, invisible war between water and stone. The water erodes the rocks, stripping away these dissolved minerals and carrying them forward. When we look at the ocean today, we see the result of billions of years of this relentless process. Chloride and sodium are the two most common minerals in seawater. In fact, together they make up roughly 85% of all dissolved minerals in the ocean. The sky is essentially feeding the ocean its salt, one raindrop at a time. So, how do these minerals travel from the mountains to the sea? They move via a planetary-scale conveyor belt. Rivers carry dissolved minerals from the rocks to the ocean, acting as the delivery system for everything the rain has scrubbed from the land. During heavy rainstorms, this process accelerates, and the dissolved minerals are swept away into the deep. But here's the core question. If the rivers are the delivery trucks, why isn't the truck itself salty? Actually, the answer is movement. Rivers are not salty because they constantly flow, flushing out minerals before they have a chance to build up. Because they're in a state of perpetual motion, salt cannot accumulate. The salt concentration in these freshwater streams remains too low for us to taste, because the water is constantly being replenished by fresh rain. And it's not just about the flow. As the water winds through the landscape, plants and soil act as natural filters, scrubbing out excess minerals before the water even reaches the coast. It's a one-way trip to the sea, and once those minerals arrive, they have no way back. What happens when the water vanishes? This is where the ocean becomes a giant salt trap. Under the intense heat of the sun, water evaporates, returning to the sky as fresh, pure vapor. But the minerals and salts stay behind. It's a one-way street. The water leaves, but the salt is trapped. Because of this constant cycle of evaporation, the ocean has grown saltier over millions of years. To wrap your head around the scale of this, consider a single cubic mile of seawater. Inside that massive block of water, there are 220 million tons of salt. If we gathered every single grain of salt from every ocean on Earth, the total amount could cover the entire planet in a layer over 500 feet thick. That is taller than the Statue of Liberty. While other minerals, like calcium, are extracted by marine life to build shells or absorbed by geological processes, salt tends to remain. This concentration of sodium and chloride makes the water undrinkable. We're left with a massive, liquid archive of Earth's erosion, a brine that simply has nowhere else to go. Down in the crushing darkness of the abyss, there is a second, hidden source of salt. While runoff from the land provides one half of the equation, openings in the seafloor allow the ocean to breathe from the inside. Water seeps into cracks in the crust and is heated by magma from the Earth's core. As this water becomes superheated, it undergoes a violent chemical transformation, losing oxygen, magnesium, and sulfates. Instead, the water picks up metals such as iron, zinc, and copper from the surrounding volcanic rock. These fissures, known as hydrothermal vents, discharge geothermally heated water back into the open ocean. These vents are most common near volcanically active zones, in deep ocean basins, or where tectonic plates are pulling apart at mid-ocean ridges. When this water is released, it carries additional minerals into the sea, creating massive hydrothermal deposits on the rocks. It's a violent chemical engine driving the salinity of our seas from the bottom up. Now, let's pivot. We've explored this massive, planetary-scale salt trap, but it brings up a critical question. Why don't our lakes and ponds do the same thing? If the same acidic rain falls on the same rocks and the same sun evaporates the water, why are most of them still fresh? It's a mystery of the missing exit. For instance, did you know that an astronaut's sweat is technically saltier than the ocean? It's a wild detail that shows how biological systems can concentrate salt even more intensely than the entire Atlantic. Some places on Earth actually break the rules of the freshwater system. In extremely hot and dry regions, rivers can become salty because water evaporates faster than it can flow. In these cases, the water vanishes into the air, but the minerals stay behind, turning the river itself into a saline environment. It's a concentrated flip of the ocean's salt trap. We see this happening in real time with the Colorado River and various rivers in Australia, which have naturally high salinity levels. In these areas, the water doesn't just move toward the ocean, it struggles against a relentless evaporation process. When these rivers flow into a closed basin, a place with no outlet to the sea, they create what we call a salt lake. Instead of a white sand beach, you find a landscape of concentrated minerals, like the Dead Sea, where the delivery system has essentially stalled and trapped the salt exactly where it started. What if we just stripped the salt away? It sounds like a dream for someone who hates the taste of seawater, but the reality would be a global catastrophe. If the oceans suddenly became freshwater, most marine life would perish due to osmotic shock. Without the external salt to balance their internal fluids, their cells would simply absorb too much water and explode. But the disaster is not just biological, it's atmospheric. Without salt, the Gulf Stream, the great conveyor belt of heat, would shut down, triggering massive climate shifts. We could be looking at a potential new ice age in Europe. Furthermore, the surface of the water would change. Without salt to regulate the ecosystem, toxic algae blooms could explode, turning the blue ocean into a green, slimy mess. The salt is not just a flavor, it's the structural regulator keeping our planet's biology and weather systems from collapsing into chaos. Wait, if salt is constantly being added, why hasn't the ocean turned into one giant, solid block of salt? It turns out the Earth has its own natural thermostat for salinity. First, marine life plays a huge role. Many organisms use salt to build shells and skeletons, effectively locking the minerals away from the water. When rainwater reaches the ocean, specialized organisms extract minerals like calcium through biological processes. Then there is the deeper geological side. Excess salt eventually sinks to the ocean floor, forming solid evaporite deposits on the seabed, removing it from the circulating current. Then tectonic activity recycles the salt. As the Earth's crust shifts, some of the excess salt is pulled back down into the mantle through subduction. It's a massive planetary-scale cleaning system that prevents the oceans from becoming oversaturated. Look at the Baltic Sea. It's a fascinating example of how the balance of rain and fresh water is constantly shifting. Because of the massive volume of fresh water flowing in from surrounding rivers, the Baltic Sea is significantly less salty than the open ocean. It's a delicate, localized equilibrium where the influx of water dilutes the salt, creating a unique environment that differs from the global average. This variation shows us that while the ocean is a giant salt trap, geography can prevent a body of water from reaching that same concentrated level of brine. The salt in our oceans is not just a seasoning or a random byproduct of nature. It's a billion-year-old liquid archive of Earth's history. From the invisible acid in every raindrop to the superheated vents in the crushing dark of the abyss, every grain of sodium and chloride tells the story of a planet that is constantly eroding and recycling itself. We've seen how a layer of salt 500 feet thick, taller than the Statue of Liberty, is the only thing preventing our climate from freezing and our marine cells from exploding. It's a delicate balance between the flowing rivers that deliver the salt and the deep geological sinks that remove it. But as our climate warms and evaporation rates shift, we have to ask, how will this ancient equilibrium change? And what happens when the salt trap begins to shift its balance?